So now that we've looked at the angular part and realized that it's just the spherical harmonics that are the same solutions to the rigid rotator, and now we've talked about them in a little bit more detail in angular momentum, we need to come back to the other half of the equation, the radial part. So remember, we took our wave function that depends on all three variables, and we separated out things into the radial part and the angular part. And now we know that the angular part is the spherical harmonics. Okay, and so if we look at just the radial dependence, just the R dependence, we can go back, if you go back a couple of videos, we had something that looked like this. So negative h bar squared over 2me r squared, ddr, r squared, dr, first derivative of the radial part, plus a bunch of constants, negative h bar squared times L plus 1 over 2me r squared. This is relying on the fact that we now know the solution to the angular part. Minus e squared over 4 pi epsilon naught r minus e times r of r, all of that equal to 0. So this is a differential equation that looks a bit more complicated than ones we've seen before. And yet again, we're not going to go through how to actually solve this. Instead, we're just going to look at the solutions. So the key points of our solutions. Number one is that when we solve, we saw that energy was part of this. We get the energies, and they depend on a quantum number n. So we get quantized energies that depend on the n quantum number. And this is usually called the principal quantum number when we're talking about the hydrogen atom. This is similar to the n that we had for the particle in a box, but completely separate problems. So they're each their own thing. But the energies are equal to a bunch of constants, minus me e to the fourth over 8 epsilon naught squared h squared n squared. Or we can rewrite this, if we write it in terms of h bar squared, we get negative me e to the fourth over 32 pi squared epsilon naught squared h bar squared n squared. Right, so these are equivalent. And one thing that's slightly different from the particle, or similar to the particle in the box, is that unlike the angular momentum quantum numbers, the principal quantum number n starts at 1. So there is no n equals 0. Right, so that's not allowed. We have to start at least 1. One way we can simplify this is that we have, this is a bunch of constants over n squared. Right, that's the key point here, is that it's quantized. There's a bunch of constants here. It looks a lot more complicated than it is, though, because this is just a number over n squared. And so we can slightly simplify this if we define the Bohr radius a naught as epsilon naught h squared over pi me e squared. We can simplify this a little bit, which is equal to negative e squared over 8 pi epsilon naught a naught n squared. Okay, another part of the solution is that n must be greater than or equal to L plus 1. And that's part of the solution that we get. Or we can say that L can equal 0, 1, etc. up to n minus 1. So for any n value, we can have multiple L values, but say if we have n equals 1, we can only have L equals 0. If we have n equals 2, we can have L equals 0 or 1, etc., etc.